Very good morning to one and all. We have come to the last day of this 5-day online international workshop on role of artificial intelligence, applications to emerging technologies, organized from 10th to 14th June 2025, and which is being hosted by Department of Electrical and Electronics Engineering, P.V.P. Siddhartha Institute of Technology. So our today's resource person is Abdul Karim Sheikh, PhD scholar, University of Michigan. He is now going to take a topic on role of AI in cybersecurity. So already we had an introduction with Karim and we have seen his presentations yesterday. So over to Karim, you can hand over the session.
Thank you so much, ma'am. And yeah, nice to see you, everyone. It's a pleasure meeting with every one of you. It was yesterday. It was a great meeting, and it was a great time, and I felt really good. Today, I'm going to discuss about a few interesting topics. Yesterday, it was something else, and today, it is really something. So. Without further ado, I want to directly jump into the presentation. Let me see.
I'm stopping the presentation, Karim. Just a minute.
Sure, ma'am. Show from the beginning. I hope everyone can see my screen. Ma'am,
Yes, yes,
can you
Karim.
see my screen?
Yes, yes.
Yes, ma'am. So, good morning, one and all. Here I am again. Today, I'm going to talk about the role of AI in cybersecurity, as well as my research area, which is security vulnerabilities of industrial robots in sensing system. So, this is going to be half, and the security vulnerabilities of industrial robots. It's going to be the other half. So, without any further ado, I just want to jump in. Let me check. Yes. So here are the contents for today. So first part is the cybersecurity of which is AI in cybersecurity. So I want to talk about the automotive field because I'm in the Michigan's. I'm in the automotive hub of whole USA, which is Michigan. So here everything is related to automotive. Even though if you're dealing with robotics, it's related to automotive. Even though if you're related to FPGAs, it's with automotive. Even controllers, sensors, actuators, motors, batteries, BMS, even the charging stations, everything is related to complete automotive because uh, almost all the manufacturers of automotive OEMs are in Michigan state. So that's why my today's concept of discussion is automotive cybersecurity. So in this one, I want to start with in-vehicle networks. Then I want to go in detail about CAN, which is control area network. It's one of the interesting networks in the automotive field. The next one is security of in-vehicle networks. So we are talking about CAN. So security of CAN. The next one is physical fingerprinting, which is the actual defense mechanism built based on deep learning models. And the graph-based IDS. This is also a deep learning based defense mechanism for this security against cyber attacks on automotive vehicles. The second half of today's session, it's going to be on industrial robots. Yesterday already we discussed about industrial robots. So I want to take the discussion further, and I want to explain what exactly I am doing, what my research is in. And I published my master's thesis, and I published a paper recently. So I'm gonna share both of them with you, and yeah, we can discuss those things. Those are pretty interesting. Actually, that paper took 8 months to complete. So it's really interesting concept. So first of all, let's start with automotive cybersecurity. So this is the concept that I worked on here in USA for the first time. So I worked on this concept for more than let's say how many years? I worked on this concept more than 1.5 year or 2 years. So yeah, I learned a lot. I built a lot of test benches based on automotive cybersecurity, and yeah, I built the defense mechanism with the help of my team and my colleagues. It's great. Let's discuss those things. So first of all, inside the automotive vehicle, there will be sensors, there will be actuators, and there will be networks. Our priority is only networks because in the especially my priority is only networks. So that's why here comes the in-vehicular networks. So in this slide, what you guys are witnessing is the complete automotive network. It's not only CAN, it's not only automotive internet, it's not only lane, it's not only flexway, it has every single network. So and the legend is here. So can low, can high, and there is flexway, there is automotive ethernet, there is lin. So here these blocks are meant for ECUs. So ECU stand for electronic control units. So each ECU is meant to control a couple of functionalities. Let's say there is an ECU called body control module, which is meant for your infotainment and your dashboard, the speedometer and the throttle that you see on screen, and the notifications, everything. So these all comes under body control module. So that is called as an ECU. So likewise, we will be having multiple ECUs in a single vehicle. Sometimes this ECU count is crazy. I mean, sometimes it goes up to 70, 80. And having a proper communication between all these ECUs, it's really mandate. So that's why we have multiple networks. So I'm not gonna go into historical part of these networks. So I just wanna show you this is the actual the current state of in-vehicular networks. So the current state of in-vehicular networks, they have everything. They have CAN. Within the CAN, they have a high speed CAN, they have low speed CAN, they have what we call automotive Ethernet, and they have LIN, they have FlexRAM, uh, and they have most as well. So these ECUs are communicated through this network, which is here low speed CAN bus. So this low speed CAN bus is connected to gateway. So gateway is you can consider it as a media converter, a translator. So it translates a data which is there in CAN into automotive Ethernet, and it takes automotive Ethernet data and converts it to CAN. Otherwise, it takes the data from FlexRay and it converts it to all other available networks within the vehicle, because we have to establish a centralized communication network which creates the bridge between all the communication medias. We have multiple, and there should be one question. Yeah, there are multiple networks. Why we are not using only CAN? Why we are not only using only LIN? Why we are not going for only automotive Ethernet? Because each network has their own advantages as well as disadvantages. It has its own pros and cons. So CAN it is actually nowadays CAN is almost 70% of the vehicle is equipped with CAN network. Rest of the 30% is divided into automotive Ethernet, FlexRay, LIN. Whereas LIN is the least costly network. I mean, this is the cheapest network in the whole vehicle. After LIN, CAN, and CAN can do most of the job. We have LIN. It's cheaper. Why we are not using that? LIN, it's cheaper, but at the same time, it can't carry enough data to transfer from one issue to other issue. Whereas CAN, yeah, almost 70% of the functionalities can run on CAN. The data packet length, the data packet size that they want, can deliver all those functionalities. Whereas automotive Ethernet, nowadays we are witnessing ADAS features. Let's say line assistant. So vehicle will change line automatically, and like there's one more feature called steering assistant control, and there's one more feature called adaptive cruise control. There's one more feature called adaptive braking system. So these all functionalities, the data pack length requirement is too high that CAN cannot handle and LIN cannot handle. So we need a high speed and high capable and high bandwidth network required, which is Ethernet. So we can't use the regular Ethernet within the vehicle. That's why we can go with automotive Ethernet. Actually, this is not completely new. It is inspired from Ethernet. So let's go deep into CAN. So let's see. So here is the CAN frame format. Right now we were discussing about CAN. We were discussing about data packets within the CAN. We are discussing about the data, but here is the actual format in which the data is being stored. So this first part is meant for the start frame. The next part is meant for the attribution. So this attribution contains actual message ID, as well as it contains what we call the hierarchy of the messages. The priority of each message is stored in this attribution bits. The next one is the control. So it is going from where to where. The other one is the next part is the data. So here is the data part, and the next part is the CRC, which is the cyclic redundancy check. Most of you are already aware what is cyclic redundancy check. And the next part is the ACK, which is acknowledgement bits. The next one is the end of frame. But if you guys observe closely, there is no source ID. There is no source information. So let's consider here. Let's consider this is our vehicle. It has multiple issues. One is braking issue. The other one is speed control issue. The other one is steering issue. It can be a BCM body control module. It can be a telematic issue. These all issues are communicating to each other. The best part here is CAN is a broadcast network. So it cannot send the data to a particular issue. It can send the data on the network. So it's like WhatsApp group. So if you send a message in the group, it'll be delivered to everyone. That's called broadcasting, data broadcasting. But if we go back here, within the data broadcasting, we don't have source information. We don't know. We got the data. I mean, every EC got the data. Let's say here, in here, breaking issue sends the data that the steering control issue sends the data that steering is turning up to this angle. So that data is already sent on the CAN network. But who's going to receive that? Which is everybody. Every issue will receive the data, but they don't know who's sending the data. Whether the data came from string issue, whether the data came from breaking issue, whether the data came from issue 1 or the data came from issue X. They don't know. That's where the vulnerability comes into picture. Whenever there is a source information, a external issue, which is issue 4 here, which is labeled in red. So this issue 4 can act as an attacker, and it can send the same data which is supposed to be sent by infotainment issue to control the braking, or which is sent by your braking paddle. Let's take an example. We are on a highway, and we are going at around 80 miles per hour. I mean, in terms of kilometers, it's around 120 kilometers per hour. I mean, on a highway, it's chill, right? So it's 120 kilometers per hour is nothing. So we were going at 120 kilometers per hour. Suddenly, brake has been applied. In fact, driver didn't apply the brake. There was no malfunction within the vehicle. There was no brake failure. Everything is good. But the brake has been applied. What happens to the vehicle? So there is a high chance that vehicle will flip over. The vehicle will rotate, or where vehicle will hit the divider. It can lead to an accident. But that data was sent by an attacker. That's exactly what this diagram is showing. This issue 4 can send the same data, which is responsibly sent by other issue, but issue 4, which is the attacking issue, sending the data. But the whole network, it considers that the data is authentic because there is no way to verify. So this is the actual issue that Canvas is having. So in our lab, under Dr. Hafiz Malik sir, we are addressing this issue with the help of this something called IDS, which is intrusion detection system. So this IDS is not one part. It's mixture of the three parts. It can work alone, or it can combine all together, and it can work all together. So the first method is the physical fingerprinting based IDS. IDS, it's intrusion detection system. Okay. Next, behavioral fingerprinting based IDS, vehicle physics based IDS. So in today's session, I'm not going to discuss about physical vehicle physics based IDS. I'm going to discuss about vehicle fingerprinting based IDS and behavioral fingerprinting based IDS, because based on these two, we can clearly say whether uh, the message is authentic or it's not. Whether this message is sent by an attacker or it's an authentic issue sent data. So to verify that, most probably these two, one of these two or combined of these two is enough. So let's discuss more deep into what is meant by physical fingerprinting. Actually, when I discuss about this physical fingerprinting, even I didn't know that I already worked on this before I came here. I already worked on physical fingerprinting back in India, and that was the patent that I was discussing with you yesterday. Let me show you something. Where is this paper? Hmm. Wait a minute. Yeah, it's in the Google Scholar. My profile. Stop presenting. Let me present something else. Yeah, I guess everybody can able to see the screen, right? So
Yes.
this was IEEE magazine, IEEE Power Electronics magazine that I was able to publish during my junior research fellow duration in Mahindra University. So here is my Professor Sridhar Madishetty, along with the Professor Dr. Sukumar Mishra from IIT Delhi. So the idea behind this whole project was, this is the actual solar PV array. So within this array, if one of the panel is faulty, there is no way to find out that particular panel. There is no way to localize that particular panel. So it's really difficult for engineers, for technicians, even for the whole, what we can say, the whole team to figure out which panel is faulty. So there are multiple methods out there, but that time it was a very interesting fact. That time we were having a challenge of find a solution without using voltage sensor and current sensor. It's tough because we the idea behind is, I need to find out the panel which is faulty, but I shouldn't use the voltage sensor and the current sensor. So uh, that time IIT Delhi, IIT Kharagpur, and there is one more IIT, IIT Goa, I guess. Those all were working on this concept, but uh, I just joined and I came up with my own solution. So here is the IV and PV curves of solar panel. So this IV curve tracer during healthy condition, and this is during a panel under fault, and this is during a panel under fault. So this dip, even though this is a panel fault, if within a string means like a couple of panels are connected in a series. Let's say there are 10 panels connected in series. We are trying to capture the IV and PV curve tracer. Our expectation is to see these curves, but we are looking at these curves. So there is a dip, but based on this dip, can we able to identify which panel is faulty? By simulation, it's impossible, but in real time, it is possible. That's my second patent. So each each of individual panel, they have their own fingerprints. They have their own unique noise. What is meant by fingerprint? I'll go back to my presentation slides and I'll be explaining what is meant by fingerprint that I'm talking. But each solar panel has their own fingerprints. But it's not an easy job to extract those fingerprints very easily. So that's why we have used deep learning models to extract those fingerprints from this signal. It was a really tough job because to plot this data, the duration of time that we were having is just 12 milliseconds. So we will get data just for 12 milliseconds, sometimes 16 milliseconds, not more than that. So we captured the data which is coming between 12 and 16 milliseconds, and we plot this one, and based on this one, we ran our deep learning model, we trained our deep learning model, and we deployed our deep learning model. It will identify which panel is faulty. If there's a dip, it will exactly say which panel is faulty. That is using deep learning model. But this paper is based on actual hardware. I'm electrical engineer. I mean, my background is in electrical. My diploma is in electrical. My BTech is in electrical. So even I worked as a solar embedded engineer in Mahindra University. So here is the solution that I built. So whenever the solar panel is faulty, that bypass diode will be activated. Whenever if solar panel is healthy, let's consider from healthy to faulty. When it's healthy, the bypass diode will not be activated, and this negative is going to positive, and positive is going to negative. So in that case, we will get huge negative voltage around this what we call DC-DC converter. So there's a reverse bias diode, and which will block the whole thing. But whenever there is a fault on the panel, so the whole power will be passed through this diode, because that's why it's called bypass diode. So instead of blocking the whole, instead of creating the open circuit, this bypass diode will close the circuit, and the current and voltage current pass through this diode. But whenever this diode is activated, there will be small cut in voltage. We all know whenever a diode is turned on, there will be a cut in voltage. That cut in voltage sometimes lies between 0.7 to 1.2. I know that's not easy, and our idea was to not use any voltage sensor, current sensor. So we were using DC-DC converter, which is the boost converter, which converts the voltages from zero point 0.5 to 2 volts up to 5 volts. So the output is either 5 or 0. If the voltage is below 0, the output is 0. If the voltage is between 0.5 and 2, the output is 5. So based on that, we were able to find out which panel is faulty. I know I'm a little out of the track. Let me jump back to our today's topic, which is, where is this? Yeah, it's here. Yeah, why I was went back to that explanation is this fingerprinting. I'm just talking about this fingerprinting in automotive right now. I talked about this automotive this fingerprinting in solar, but this fingerprinting is there in every single hardware. That I was not aware until I did that project in Mahindra University, detecting solar panels, faulty solar panels. So whenever there is a signal passing from an ECU or an electronic device, there will be fingerprint. So what is mean by this fingerprint? There will be noise. In the other sense, in actual electrical and electronic signal terms, there will be a noise, and that noise is called transition noise. And this transition noise is unique for every individual device. Let's say Bosch is manufacturing ECUs for Ford. I already used the example of Ford. Let's not blame Ford for every single example. Let's consider BMW. So Bosch is manufacturing ECUs for BMW, and within the same manufacturing batch of Bosch for same vehicle on the same day in the same batch, two consecutive ECUs will not be having same fingerprints. There will be difference between those two ECU fingerprints. That unique this fingerprinting is. So we can for this automotive cybersecurity, we are catching this fingerprints with the help of sophisticated analog to digital converters, and our sampling frequency is it's way too much. It's I guess around 150 to 200 mega samples per second. So from ECU, we are extracting the signal, and based on the signal, and this signal has fingerprints. So we are extracting this fingerprints. Based on the fingerprints, we are extracting the actual features to train our deep learning model. So once the features are extracted, we are training our model, and this deep learning model identifies from where this data has came. So after the feature extraction, there is a deep learning model, and that deep learning model decides this data came from issue 1, issue 2, issue 10, or issue number n. So that is called source identification. Actually, we are attaching this source identification to canvas data. That is not there as part of actual can data frame. So we are adding this source information to the CAN data. And the other one is the source authentication. So first one is identification, source identification. The next one is data authentication. Now it will verify whether the data is authentic or not, whether this data has to be processed or this data has to be flushed. So that's called data authentication. So this is how the physical fingerprinting based cyber security defense mechanism works. Okay, next. So here is my team. Like couple of them are from India, a couple of them are from Pakistan, and yeah, a couple of them are from Bangladesh and Middle East. So here's me, and here's Jyotim, and this test bench is actually demonstrating the functionalities of automotive with an automotive can. So these two small displays that you see on the screen, one of these displays is meant for infotainment. So with the help of that, this white block is a motor. It's a permanent magnet DC motor. So we can control the speed of the motor through this infotainment, and this data is going to the ECU through CAN bus. So the message is in the CAN format. Next, not only the engine, there is wiper, there is steering, there is headlights, there is brake lights, there is trunk, there is boot open and closed. And wait, here are the culprits. So this ECU and this ECU, I didn't time this ECU, but this ECU is actually an attacker. It creates a DOS, which is the denial of service. It creates an attack called replay attack. So the DOS attack is, it will flood the network. So it will flood the network with high priority data. Let's say the attribution ID, which is 0x00, has the highest priority. Yeah, it's a fact that within the CAN network, in the arbitration IDs, the lowest value of ID will be the highest priority. So it's obvious that 0x00 will be having the highest priority. So if an attacker enters the network and he flirts with 0x00 with multiple entries of data, the network will be freezed. There will be no other data, there will be no other issue that can communicate. Let's say the infotainment is sending like motor to run at 60% of its speed. No, it can't, because the network is already flooded with automotive canvas data with what we call the highest priority device attack, highest priority flooding. So that is called actual device attack. The other one is replay attack. It's exactly what we discussed in our previous example earlier. So it can mimic any one of the issue, and it can generate the data, and it can like the other issue will listens to this issue. So that's called replay attack. And there's a spoofing. There are multiple attacks. And on the right side, here is the actual defense mechanism that we built. So this feature extraction deep learning model, yeah, this test bench is meant for that physical fingerprinting. So 1, 2, and 3, these three guys built this one, and my team built this one, and I was the leader. I was the lead for the whole team. Why I'm mentioning I was, because now I just step out as the lead of the whole team, because actually it was too much responsibility. I it was overwhelming. So I stepped out of lead position. Next, the next way of defending the defending the attackers to enter into the network, which is called graph based IDS. So instead of extracting the fingerprints, instead of using sophisticated what we can say that A to D converters, sophisticated processors, so we can just able to use the data. So actually, this graph-based IDS comes under behavioral-based IDS, which is the behavioral-based intrusion detection system. So once we get the data from a vehicle, we are at one of my senior. He graduated from his PhD from a lab. So he built this whole system. So he captured this data from the actual vehicle, and he convert this data into graphs. You can see that these are Mull and Moore graphs, but no, these are not. These are just graphical representation of data flow. So these are like message IDs. These are attribution IDs. So from which attribution ID data is going from this ID to this ID, this ID to this ID. So he convert this data into graph, and based from the graph, he was able to figure out a pattern. So here's the thing. Uh, I'm at a point of discussion where now I can say that how we can able to use deep learning, how we can able to use this AI, the part of AI models, which are either machine learning or deep learning or reinforcement learning. The first point that we have to do is we have to observe the pattern. If there is any fault, or if there is any it's I'm just talking about fault, or if you want to implement a deep learning model into something, first observe a pattern. There will be a pattern in every single aspect. Let's say I'll take an example of PPI controllers, which are like universal controllers for every single system. It's not only for electrical, it's meant for electrical, mechanical, it's meant for robotics, it's meant for automotive, it's meant for everything. But deep learning can replace our traditional PPI controllers. You can ask a question, why we have to replace here. It's just a simple formula. We can place the formula where on the other side, like, we have to build a network, we have to build a model, we have to train the model, we have to test the model, and we have to run multiple test cases, and then we have to deploy it, and it's a lot of computational energy. But there is a catch in PPI controllers. Whenever the noise is changing, we have to retune, we have to tune these controllers. But for deep learning model, it's already trained, so you don't have to train again and again. So once it's trained, it works way better than PPI controllers. So there is a paper, there's an interesting paper which was published by Dr. Sriranga Suprabhat. He graduated from his PhD from Mahindra University. Now he's working as postdoc candidate under Dr. Sukma Mishra in IIT Dhanbad, IIC Dhanbad. And yeah, that paper will give you a complete detail of how a deep learning model can replace traditional PPI controllers. So his research is absolutely amazing research. Next, let's come back to our discussion. So from the graph, we are extracting features. So these features are being trained and tested. And guys, if you are sorry, everybody, if you have any doubts, just stop me in between and you can ask doubts. Like, you don't have to wait until all the way till the end. Okay. Yeah. So first this data goes to training and testing. Once the training and testing is done, the model is built. So this model verifies whether there is an attack within the network, on the network, or there is no attack. So here is the graph that he got after his research. This attack free, this is DOS, this fuzz attack, this spoofing, replay attack. Actually, he did a lot of other attacks. He just mentioned these couple of these attacks here. So we can turn a regular data into a really interesting graphical pattern, and based on that graphical pattern, we can build a deep learning model, and based on that model, we can identify whether our system is under attack, cyber attack, or not. This is what I understood from this whole concept, and that's what I'm doing, because Right now, in my thesis, in my PhD work, I'm trying to observe the patterns. So once observe the pattern, my job will be like almost my job will be done. The next part will be data. Once I get the data, as I mentioned, like 80% of the job is done. Next, I have to just try and test and deploy the model. That's it. Next, so let me take just uh small break of for water. Yeah. So usually, what happens to actual research is first they'll scare you, then they'll like calm you down by showing like the defense mechanisms. But till now, I have shown you the defense mechanisms. But here is the actual scary part. So uh, the other part of the session is cybersecurity of industrial robots. So how the security is important to an industrial robot. As I already mentioned, like industrial robot is a crucial part of actual manufacturing assembly line industry. So as we have already seen like classification of industrial robots, but this is the most sophisticated graphical representation. So we have industrial robots based on kinematics. They can be Cartesian robots, they can be star robots, articulated robots, delta robots. Based on control methods, yeah, it's simple: open loop and closed loop. Based on power, electric, hydraulic, pneumatic. And based on degrees of freedom, here I mentioned just two, which is 6 degree of freedom, 4 degree of freedom. There are multi-degree of freedom. There are 2 degree of freedom. There are 8 degree of freedom. There are 10 degree of freedom. There are a lot. Next, collaborative robots, which is the cobots. So here are some common components of industrial robots. Um, this part of the robot is called base, and this is the shoulder, elbow. The whole part is a manipulator. Here is the wrist, and this is called the end effector. So end effector can be anything. End effector can be a gripper. End effector can be a suction. End effector can be a magnet. End effector can be anything. So this part, I mean, this particular robot is having multiple sensors in it. It has torque sensor at every joint. It has a vision sensor at the like end effector. It has inertial sensor, which is the accelerometer and gyroscope sensor. There will be a rotary encoder at each and every joint to give us information about the what we can say like the rotation angle and position of each joint. And there will be current and voltage sensor within the control box. So here are just a couple of sensors. So here is the actual communication layer. So if you're really interested to start with want to start with actual cybersecurity, you have to figure out the attack vectors, because that's where actual research starts. Because if you know the attack vectors, so you'll figure out which way is the easiest way to attack the whole system. So for an industrial robot, there will be a physical layer, there will be a network layer. Within the network layer, there will be industrial controllers. So industrial routers. So industrial routers are a bit different from our regular routers, regular Wi-Fi routers within our home. These routers are really sophisticated, and they're more powerful, and they're more vulnerable as well. That's the downside of that. And industrial control PCs, industrial controllers, which are it can be A PLC, it can be a SCADA, it can be NI based hardware, NI based, national instruments based hardware, it can be a normal controller, it can be anything. So here is the controller. This controller is for robot. This controller is for automation. So within the physical layer, we have the controller. We have actuators, we have sensors, we have teach pendant. Teach pendant is something through which we can control the robot. We can train the robot. We can assign a task to the robot. Whereas for sensors, yeah, as we have already seen, they're they're actually really a huge amount of sensors are deployed in an industrial robot, and there will be actuators. There will be permanent magnet DC motors. There will be servo motors. There will be stepper motors. There will be suction. There will be hydraulic controls. There will be a lot of actuators within this one. There will be linear actuators. There will be a lot, and attacker can attack at every single point. Attacker can enter into sensors, so he can malfunction sensors, through which he can enter into system. The other part is the actuators. He can malfunction the physics of actuator, and he can enter into system. And controller, yeah, there are multiple ways to hack controller. Where teach pendant, yeah, it'll be having it'll be connected to Wi-Fi network, or sometimes it'll be having USB ports, and it'll be having some ports for data communication. But that ports will create an entry point to an attacker. Next, industrial routers. There is a scary research. There is a interesting and as well as scary research which was done by a professor from IIT Italy, Italian Institute of Technology Italy. In his paper, he said that the industrial routers are so vulnerable that we can control a robot either from India or from USA. We can control a robot which is there in Japan, in some industry, and working for some, let's say, some welding or some sorting or some cutting. So we can control a robot which is there in some other country. And he listed out all those IP addresses of those industrial routers, and with the help of those router IP address, we can able to hack the robot. But still, those companies are not taking responsibility to secure their systems, because we have IT, we have OT. IT is meant for information technology, and OT is meant for operational technology. Operational technology, yeah, one of the examples is robots, automation. The security that is there for IT, it's not there for OT. OT is not secured as IT is secured, because IT has so many security systems. But OT, like the breach of OT network, OT security system is absolutely easy. So that's why they're not taking care, because there are no much solution out there. So it's our responsibility to build a really sophisticated secured system for OT networks or OT platforms. Not only networks, we can work on OT sensors, we can work on actuators, we can work on controllers. We can, yeah, we can work on one particular part. At the end of the day, uh, if we all combine together, it's a whole solution that industry needs. So here are the couple of sensors that I have listed in my research article recently. But these are just almost 11 to 12 sensors. But in my thesis, I list out around 25 sensors, I guess. It's more than 20 sensors. So there are multiple types of sensors. So here's a tactile sensor. It mimics the human touch. So actually, these tactile sensors will be deployed within the robotic arm, or within the gripper of the arm, gripper of the actual robotic arm. Next, inertial sensor. As I already mentioned, this inertial sensor is meant for the acceleration These meant for vibration, these meant for the acceleration, and like what we can say, velocities, accelerations and positions. Next, current sensor, voltage sensor, as we know that. And the torque sensor, it measures the torque which is applied on each individual joint. Because if we measure the torque, we can identify like how much weight we are carrying, because torque is directly proportional to our like current, and based on current we can figure out the weight, or we can come other way, based on weight how much torque is applied, and based on torque how much current is drawn from our robot. Next, rotary encoder to find out the position of the joint. Next, a force sensor. Laser sensors. Laser sensors are meant for the distance measurement, and they are meant for object detections as well, not only the distance. And ultrasonic sensors, yeah, these are purely meant for distance measurement and obstacle avoidance. There will be acoustic sensors. These sensors are meant for environmental awareness. So robots working in industry, they should have the environmental awareness. So that's why they use acoustic sensors. The next sensor is a pressure sensor. We all know that. The lidar. So it gives a 3D map of the environment around the robot. And photoelectric sensor, it's for object detection and the distance as well. And vision sensor. But these all sensors are vulnerable to the sensitivity of temperature. Couple of sensors are sensitive to temperature, couple of sensors are sensitive to EMI, which is the electromagnetic interference, and some sensors are vulnerable to acoustics, which are external acoustic signals. It can be within our audible range, or it can be out of audible range. It can be exactly lies after our audible range. And the light interference. So here's a diagram. I mean, sometimes I feel a little proud of looking at this diagram, because it took almost around 2 weeks to build this diagram. So this diagram shows the limitations, biases, faults, vulnerabilities, everything in a single frame. Is this diagram is it explains almost 70% of my paper. And so in the first string, so I call it as ring chart. So in the first string, this is the industrial robot. So it has so I here I listed almost 8 sensors, and rest of the 6 sensors are here. So after these 8 sensors, the gray part is for limitations. So limitation is the operational limitation. Let's say vision sensor. I can give a simple example of voltage sensor for voltage transitions. Whenever there is a voltage transition, voltage sensor is of no use. Thank you so much for your comment. Next, let's consider the inertial sensor. There will be a calibration drift. Once we start the initial sensor with a calibration and initial data, and after a certain time, because of wear and tear, because of a lot of other factors, the drift, there will be a drift within the calibration. So that's called calibration drift. Whereas this the orange lines, these are biases. So these are in between limitation and fault. And these blue lines are actual biases, are actual faults. So vision sensors, actually every sensor mentioned here, they have temperature sensitivity. So if there is too much temperature, vision sensors have vision sensors can be faulty. Current sensor, obviously they have the current range. Voltage sensors, tactile, torque, rotary, inertial and laser, every sensor is sensitive to temperature. Whereas EMI is no, like there won't be any impact on vision sensor, but there will be impact on current sensors, because in industry they they don't use current sensors of non-isolated form. They use current sensors of isolated current sensors, of a form which is called isolated current sensors, because within the industry the currents will be too high. So this is the same principle that is there in the clamp meter, which we use in like uh, our regular labs. So this current sensor will be having an impact, uh, fault impact, because of this EMI, electromagnetic interference, and even voltage sensor will be having EMI. Whereas torque sensor will be having a sensitivity called cross coupling. So let's say in one of the wire, data is going from, we can say that laser sensor. The laser sensor data is going to controller. Here, the torque sensor data is going to controller. So if the wires are close to each other, there is like a very little distance. So I'm just going back to theory. So which is, whenever a conductor flows, there'll be current flow through a conductor. There'll be magnetic field deployed by the conductor. So that magnetic field, if that magnetic field interacts with the other magnetic field of the let's say laser sensor or inertial sensor, so the data will be disrupted. That's called cross coupling. So in the same way, there will be there is hysteresis, there is crosstalk. So this blue are meant for the faults, and the red is meant for actual vulnerabilities, which are, an attacker can actually access these vulnerabilities, and he can deploy cyber attacks on the sensors. So through acoustics, he can deploy cyber attacks on IMU. Through light interference, he can deploy cyber attack on laser sensors, vision sensors. That's what the vulnerability means, and the same theory works here. In fact, to build this diagram, I took really lot of work. This is part of my research paper, and at the end of the today's session, I'll be giving my research paper link. If you are interested, I'll be giving the other paper link as well. I mean, instead I can share my Google Scholar profile. You can see all the papers there, and my thesis as well. So I don't have much many papers, as most of the people who are in this session have. I have very few papers. I have few patents. That's it. I'm not that great. And then, and the last and final part, which is the cause effect diagram. So in this diagram, I'm trying to explain, this is the vulnerability and this is the consequence. The deceptive handling. Let's say what is meant by deceptive handling, what is meant by deceptive driven function. So let me check. Yeah, the deceptive handling is, let's say the robot is supposed to handle this, it has to carry this bottle, and it has to place it into a box. But what if this bottle is made of glass? What if this bottle is made of fragile materials? So if the end effector, the gripper, is applying too much torque, too much force on the bottle will break down into pieces. Or in some cases, it will deform. In some cases, the shape of the bottle will change. So that's called deceptive handling. The other one is deceptive driven malfunction, which is the whole trajectory of the robot can be deceptive, can be malfunction with the help of these sensors. So there are, like, I have listed 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have listed almost 11 sensors here. So laser sensor is on the top. Light, light interference. So this light is going to be a reflection, and this reflection will be turning into a wrong displacement, and that wrong displacement can turn into a mishandling of the object. In the same way, I can go with the example of I mean, I'll go with this example: acoustics. Acoustics with this called the inertial sensor. Acoustics can impact the displacement. I mean, which is the angular rate of the proof of mass within the inertial sensor, and this angular rate will impact the capacitance. And actually, why I mentioned capacitance is in this example I am considering my IMU is made of capacitive materials. So whenever there is a change of angular rate, that impacts the capacitance. This capacitance impacts the pressure, and this pressure actually, if the pressure is miscalculated, it will mishandle the object. So wait a minute. Whereas let's say what we can consider here. Let's consider the rotary encoder. So there is a EMI, there is electromagnetic interference on the IMU, the rotary encoder, and the magnetic flux density, because here within the rotary encoders, I am considering magnetic rotary encoders. So there is no physical connection between these two encoders. The only a force which is there in between is the magnetic field. So if there's a electromagnetic interference, this electromagnetic interference will disrupt that magnetic field. And whenever that magnetic field is disrupted, then it will disrupt the magnetic energy stored within the other plate of the rotary encoder. And because of that, they're going to change the velocity. And that velocity, because of change in the velocity, it can mishandle the objects, and it can mislead the robot trajectory. So if the robot is meant to go from point A to point B, it can go to point C, or it can go to point X. So that's how this cause and effect diagram works. So yeah, uh, till now this is the scary part, because till now I have just explained how scary our OT system is, how scary our actual robots, actual PLCs, everything is. But yeah, no need to worry. Like people out there working on solutions to build a sophisticated defense mechanisms to prevent these kind of attacks, and I'm one of them. So I'm trying to identify the cyber attacks within the hardware, and I'm trying to figure out the solution, inshallah. So, and that's all from my end. And thank you so much. If you guys have, if anyone is having questions, you can just go ahead. I'll try to answer your questions. If you want
Yes,
me to go back to any
participants.
slide,
Yeah.
that's also fine. I can go back to any slide.
Participants, if anyone is having any doubts, you can just ask him, and you can also unmute yourself as well. You can message in chat box. Karim, you were like discussing regarding the robotics, right? So
Yes, ma'am.
cybersecurity in robotics. So can you please tell me what are the other areas where you can see the cybersecurity effect of cybersecurity major, which is being burning now actually. Now it is being taking place, where the research in cybersecurity of any particular system is going very intense. Which area can you figure out?
That's actually a great point, ma'am, because earlier when I was mentioning about Dr. Suprabhat, his complete name is Dr. Sringa Suprabhat. So his PhD concept, which is cybersecurity of DC microgrids, cybersecurity of grids, so cybersecurity of power systems. That's where actual cybersecurity is booming right now. Because if something happens to power grid, it's the national security issue. It's yeah, like first point, like the company goes under bankrupt, and the country goes into economic crisis. So that's one of the like positions where cybersecurity. I'm thinking like cybersecurity is crucial, playing crucial role. Yes, sir. Yeah. Go ahead.
Maheshwarappa garu, yes, you can go ahead with the question. You have been
Hello?
raising your hand. Yeah, you can unmute yourself and ask the question.
Hello.
Yes, sir.
Good morning, sir.
Good morning, sir.
Very nice session, sir. Rivers.
Thank you so much, sir.
So thank you for that. Your effective, wonderful session we enjoyed.
Thank you so much, sir. And it was a great pleasure to demonstrate and showcase the work I did and what's out there. And it was a great pleasure for me. Thank you so much.
Okay, sir. Okay. Thank you. Thank you.
Thank you so much, sir.
Any other participants, if having any questions or you have any point to go ahead, like you have any point to discuss with him, you can go ahead. Yes, sir. HOD
Hello.
triple
Good morning, sir.
Yes, sir. Yes, sir.
Hello, Karim, sir.
Yes, sir. Good morning, sir.
Yes, sir. Sir, have you implemented practically this one, sir? Because little bit I joined late. Have you implemented this practically and got the results? And
This one, sir. I mean, the security of sensor security of industrial robots.
okay, sir. Yes, sir.
I
Yes,
mean,
sir.
yeah. So this one actually I'm implementing right now. So yesterday, I don't know whether were you there in the yesterday session or not. I have my own robot, and there's a sophisticated industrial robot in my lab. So I'm working on actually this part. So which is figuring out which actual physical property of environment can impact a sensor of industrial robot, and because of that sensor, how the robot will behave. So
Oh,
yeah, I'm working right now, sir. But there's a really small amount of research has been done in this domain. If anyone is interested to work in this domain, yeah, I mean, I can provide the resources, and yeah, it's completely new, sir. There
okay,
are
okay,
nobody. There are very few people who are working in this domain, and whereas
okay,
the automotive, yeah, we have already implemented this one. We have already
okay, okay,
implemented the automotive cybersecurity in real time. So we are
okay,
going to we are going for a what we call a startup.
okay. Okay, sir. Thank you, sir. Thank you. Thank you, Karim, sir.
Thank you so much, sir.
Participants, I think we have been sharing all the videos are being uploaded. All the recorded videos of the sessions from all the past 4 days are being uploaded in the YouTube. We have also given in the workshop group that YouTube link and all. And also, if any resources shared by our resource persons, will post in the group itself so that you can make use of it. If anyone like required to discuss with Karim, you can go ahead, either in the chat box or you can unmute and talk to him. And anyhow, that was great, Karim. That's an excellent session where definitely who are working in this area, it's a great insight for them. Thank you once again for taking your time for the past 2 days and sharing your work your master's work as well as PhD work with us. That's a great thing. If anyone want to collaborate with Karim, you can go ahead. You can ask him. You can text him actually. Yeah, he has given his LinkedIn link also in the message box, and also I'll share it in the workshop group. If anyone wanted any doubts, or like you, if you're going to work in this area and your research domain, you can ask him. And once again, thank you so much, Karim, for making your time and giving such an insight. Thank you so much.
Thank you so much, ma'am. I mean, actually, it was a great pleasure for me to be here, like a member of like this workshop, and yeah, it was a really great workshop, and it was absolutely amazing, ma'am. And thank you so much for providing this opportunity, and thank you so much for all your support back from 2017. Thank you so much for everything.
There is one announcement to the participants that we are having an afternoon session also by Karnakar Garu. That will be the last session of our 5 days workshop. So request all the participants to join. And as mentioned in the group, the feedback link will be shared in the Google Meet link only, overall feedback link. I'm talking about the overall feedback link of this workshop will be shared only in the Google Meet link half an hour before we closing. And also there will be a closing ceremony also at the end of our today's last session. Thank you, Karim.
Yeah.
Thank you so much.
Thank you so much, ma'am. And I have provided my Google Scholar link in the chat box, and I have provided my previous professor, Dr. Sridhar Marishetty, his profile as well. And I'm sharing Dr. Hafiz Malik. He's legend. I mean, I'm sorry to use this word, but he is. He is legend. He's my professor right now. So you can go through those papers of those two professors, and yeah, I already mentioned, like, I have only few papers, and feel free to reach out to me. I have already mentioned, like, sent my email ID in the chat box. So and anyways, Bhavana madam, she'll be sharing my LinkedIn profile with you, and let's get connected. Thank you so much, everyone, and thank you so much for being listening to my boring session for so long time. Thank you so much.
It's not boring, Karim. You should not tell that. Okay.
No, I mean, I was just kidding. I was just kidding.